Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. Tonight we're really excited to bring you Math Behind the Music, exploring the harmony of mathematics. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make those tough to teach, tough to learn concepts accessible to all my students. I'm super excited to introduce our two panelists tonight, Ellen Brown and Dr. Steve Arnold. Ellen is a T-Cube National Instructor and lives at the Pomfret School in Pomfret, Connecticut. After teaching music for 25 years, she switched over to teaching math and engineering. She was immediately captivated by the possibilities of TI technology. Ellen was a participant in TI and Ohio State University's Connected Classroom Study from 2005 to 2009 and became a TI instructor in 2010. She enjoys conducting TI workshops and is passionate about helping educators attain their goals. Ellen, thanks so much for joining us.
Here, Mike. I'm really excited to be here, Mike, you and Steve.
And a high school math teacher and researcher for 35 years, Steve has presented and published internationally on the applications of technology in math classrooms. He currently works with the TI Education Technology Product Strategy Group. Steve, thanks so much for being with us.
Thanks very much, Mike and Ellen, and greetings to everyone from down under.
We're expecting a large crowd on tonight, so your audio is automatically muted. Feel free to send any questions at any time to Ellen or Steve using the Q&A window on the right side of the screen. We'll also be using the chat window to send general messages. As a reminder, tonight's webinar is being recorded, and at the conclusion of the webinar, we'll be sending a certificate of attendance, a link for a certificate of attendance. Tonight we're going to be doing some pretty interesting things, and I think it's going to be really challenging to follow along with your handheld, so I really recommend waiting for the recording to come out, which will be in a couple days. You'll automatically get an email with that. And then you can go through the recording and your handheld or software at your own pace. That way you can pause and rewind the recording as necessary. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate in the WebEx menu, choose Audio Broadcast, and then click Join. At this point, Ellen is going to discuss our agenda.
So we already did the welcome and introductions by Mike, and then we're going to be doing the search for harmony and the math behind that, because of course that's the title of the webinar. The harmonic mean, because many students don't realize there's other means besides the one they use to figure out their grades. So we will discuss what do you mean. And then the pictures of harmony, and that brings our geometry in, and we have some cool slides on how to make the geometric mean. The sound of harmony using the TI Innovator, which is very cool, and then we're going to finish up with trying some coding and seeing if we can make these scales ourselves. Toward the end, we'll be doing the online resources and references so you can get all the files that we're using, and then we'll do a webinar giveaway, a complimentary registration for the TI T3 International Conference.
Thanks so much, Ellen. It's all yours.
Okay, so I am going to share my desktop and get our file. Take it away, Steve.
Thanks very much, Ellen. Hello, everyone. Many years ago, I became interested. I came across a little fellow called the harmonic mean, and I hadn't heard about this before. I'd heard obviously about the arithmetic mean, the one that when we talk about the mean or the average, that's the one we assume, and the geometric mean. But I discovered references to this thing called harmonic mean, and I started to dig around and started to do a bit of research on harmony in mathematics, and it turned out all sorts of interesting things. So the various activities that we'll look at in this in this webinar tonight are things that I've tried with my classrooms over the years, and it's one of what I like to think of as almost a perfect problem, because it's got the potential to span not just the various branches of mathematics, arithmetic, geometry, algebra, series and sequences, but also span the school years. There's genuine mathematical challenges and activities for students, certainly from early high school through to seniors. So let's move through and have a look at some of these ideas. So we're going to look at this idea of the harmonic mean, how it's related to its more famous cousins and what it has to do with the various branches of mathematics and music. Did you know that to Pythagoras, the 4 branches of mathematics were arithmetica, logistica, geometrica, and harmony? So we'll talk a little bit more about that shortly. We're going to begin with some examples from arithmetic. But you know, when Pythagoras talked about arithmetica, he wasn't talking about arithmetic in our sense, the manipulation of numbers. Arithmetica was the higher study of numbers, what we think of as number theory. Calculation was called logistica. So we're going to start with a couple of problems for you to have a look at and think about. And as I would do with my kids, I'd actually like to put these up for just a short time for you to have a look at. So we'll give you about 30 seconds to have a look at this.
So do your math fast.
Yes, yeah, by all means, you might like to have a go.
You can put the answers in the chat window if you're so inclined.
If you think you've got, well, in fact, I'd encourage that. We'd love to have a look at your a few possible answers, and don't be afraid to
make a mistake.
To make mistakes. Now I'm having trouble seeing where the chat window is. How do I get the chat window up?
Steve, if you move your mouse, probably under that green tab.
Yes, this green tab up here.
Yeah,
See,
yeah,
then it has the chat. There's the chat. I don't want to put it on my screen because it'll cover up our problem.
Thank you. Thank you very much. Yep.
Are we getting any answers?
Actually, I'm not seeing any answers at this stage, but that's okay.
Okay.
These problems, you don't really appreciate how sneaky and nasty they are until you actually have a go, because on first sight you think, well, that's pretty easy. But I mean, your initial instinct is to go for, okay, the arithmetic mean. So 2.5. I'd order 2.5 kilos of each. 2 kilos of oranges for $1 and 3 kilos of apples for $1. But of course, that's going to be more than the $2 that Mum gave me. So it can't be 2.5, it's going to be less than 2.5. Ellen, move on to the next problem. And apologies if you're just starting to sink your teeth into that one.
But you'll have the slide and you can try it later.
Yeah, yeah. We've got 3 problems here that, that we'd like to quickly show you. Each of them should ring some bells for teachers who've taught for a few years. They're ones you do come across from time to time, usually when you're trying to be nasty to you. No, you're trying to get them to think. So the trains leaving, entering the tunnel at the same time, travelling towards each other. We assume they're on different lines.
Let's hope.
Let's hope. So one, it takes 8 seconds to travel through the tunnel. The other takes 12 seconds. And again, the answer is not going to be 10 seconds. It's not going to be halfway. And in fact, it can't be 10 seconds because one of them gets through the tunnel in 8 seconds. So there's all sorts of interesting twists to these problems. I suggest what you think about is that the unit that they're using here is time. Let's turn the unit around and think of the unit as the tunnel length. So how much of a tunnel would the XPT
We got an answer for the other one.
Thank you. Very nice answer. We'll come back to that. How much of the tunnel would the XPT get through in 1 second? If it takes 8 seconds to travel through the tunnel, then obviously the XPT covers 1/8 of a second, 1/8 of a tunnel each second. The VFT will cover 1/12 of a tunnel. So your unit becomes tunnel, not time. And suddenly you realise that you're working with reciprocals. Move on, please, Alan. Thank you. Same problem again in a different form. 3 pipes. Sorry, go back one.
Oop.
Oop. Thank you. So pipe A can fill the tank in 4 hours, pipe B can fill it in 6 hours, and pipe C can empty it in 5 hours. And again, let's think of the unit here as 1 tank. Then in 1 hour, pipe A is 1/4 of a tank, pipe B 1/6 of a tank. So we're working again with reciprocals. Move on, please. And yes, the challenge part of that one. Next one, please, Owen. So let's think about means for a minute. And many students, certainly until they reach the senior years and start to look at series and sequences, will think there's just one mean. That's the arithmetic mean. Then, of course, we take delight as a teacher in saying, no, there's also the geometric mean. And aren't I clever that I was able to tell you? But in fact, there are lots and lots of means. And if you do a Google search on mathematical means, you'll see that there's many of them. A mean is just a mathematical process which can take 2 or more values and it returns some calculated value, which may or may not lie between the 2 values that you started with. If we're going to call it a mean rather than just any mathematical process, though, there is one proviso. What I think of as a good mean, if you put the same number in multiple times, it should return that number. So the mean of A and A should still be A. Okay, and we see then straight away that the arithmetic mean, adding the 2 numbers and dividing by 2, and the geometric mean, which is taking the square root of the product of 2 numbers, will return the same value. So 3 plus 3 divided by 2 will still be 3. 3 times 3, take the square root, will be 3, at least for positive numbers. So what about a couple of other mathematical processes? We've got 2a plus b over 3. Well, again, if a and b are both equal to 3, then what we're going to get is, that's a good mean. I don't know what it's called. It's probably got some complicated name. Look at the next one. 2 times a times b over a plus b. A little bit more complicated. So let's try again, 3 and 3. 2 times 3 times 3 is 18. 3 plus 3 is 6. 18 divided by 3 plus by 6, we're back to 3. So that's a good mean. And in fact, that's a very special mean. Ellen, next page. We've defined the 3 means here on this page using TI-Nspire. So the arithmetic mean is a plus b over 2, the geometric mean, the square root of ab, and the harmonic mean, 2 times a times b over a plus b. And Pythagoras knew of this process. He talked about the harmonic mean. There's a few different ways to calculate it, but basically, let's think about a sequence, A, B, and C. Now we know if A, B, and C are in arithmetic progression, then B is the arithmetic mean of A and C. And there's a common difference between them. Turns out the harmonic mean is the same thing with reciprocals. So if A, B, and C are in arithmetic progression, then 1 over A, 1 over B, and 1 over C are in harmonic progression. Next page, please. Let's have a quick look at some calculations. So, for instance, 2 and 3. The average arithmetic mean of 2 and 3 is halfway between them, 2.5. The geometric mean is the square root of 6. And the harmonic mean, let's try this out now. So let's do the formula. 2 times 2 times 3, that's 12, over 2 plus 3 is 5. 12 over 5, 2.4. Okay. Now, if we think back to our first problem, and Ellen, if you can quickly duck back to our first problem. There we go, that one. 2.4, if I order 2.4 kilos of each, then it turns out I will get exactly, that'll cost me $2. That's the solution to our problem, and it's the harmonic mean of 2 and 3, because we're working with reciprocals. If I add a half plus a third, then I get 5/6. What have I done? A half of a half plus a third, yes. A half plus a third is 5/6. A half of 5/6 is 5/12. And if I turn that upside down, then I get 12 over 5, or 2.4. And that will give me my correct answer. Move to the next problem. Similar deal. Let's do 2 times 8 times 12 over 8 plus 12, that's 20. Well, that gives an answer of 9.6.
Well, hang on, Steve. One of the trains takes 8 seconds.
That's right. Because they're traveling towards each other, they're covering their amount of tunnel. The solution here will be half of that. But that's not obvious until you think about it and you apply common sense. So in fact, the harmonic mean of 8 and 12 is half of 9.6, 4.8. And that's how long after that number of seconds that the trains will meet. Again, all of these materials will be available, and there's a website that takes you through all of these problems. So if we, Ellen, move back to where we were. Thank you. Now, these sliders are there for students to play with. The whole idea to try out different numbers and get a feel for the different means. If you play around with them, something you'll notice fairly quickly is that there is a relationship which is quite famous, quite historical, and quite important for all sorts of applications. For any two given non-equal numbers, the arithmetic mean is always the greatest, the geometric mean is in the middle, and the harmonic mean is always less. In other words, they're always in that order. So between 4 and 28, you'll find the harmonic mean will be the least, the geometric mean the middle, and the arithmetic mean the higher value. So all sorts of interesting explorations and questions for kids to play with and ask. Move on, please. Now, the Greeks had no algebra. That didn't come until the Arabs centuries later. Greek mathematics was geometric. Okay, construction, everything was about construction, even multiplication. They didn't think of it as we do, as this abstract idea of 3 times 4. When they thought of multiplying two numbers, they thought of the area of a rectangle. And they would construct this area. They say you'd have two segments at perpendicular to each other and the area of that rectangle. So what actually got me started on, really intrigued me when I started to dig deeper into this harmonic mean, was that I found these applications of it, and I knew that the Greeks were big on their geometry. So I thought there must be a geometric construction for the harmonic mean. the geometric construction for the arithmetic mean is very, very simple. If you think about a circle, for instance, as shown here, suppose we've got a circle that's got the diameter AC, with B as some point in between. Then we've got a length AB and we have a length BC. If we add those and divide by 2, what you get is the radius of the circle. So you can easily construct the arithmetic mean of any two numbers by gluing the two segments together, drawing a circle around that diameter and marking off the center of the circle. Or more simply, just gluing the two segments together and bisecting that interval. You don't need the circle to do it. The circle comes in useful for the other two. Because I guess something I knew at this stage, and many of you will probably know, and that is that the length of so look at the point B, where the segment AB joins BC. Draw the perpendicular at B so that it meets the circle at D. Now that perpendicular length, the square of that is equal to the product of the 2 feet, the feet at the bottom. So in other words, AB times BC will equal BD squared. And that's just another way of saying that BD is the geometric mean of AB and BC. So it's a lovely way to construct the geometric mean. Once again, glue your two segments together, draw a perpendicular, construct a circle, and you've got yourself the geometric mean. And you can see from this actually visually, immediately, the length OD, the radius of the circle, must always be longer than BD, because it's the hypotenuse of the right angle triangle OBD. So there you've got that relationship. But now we get one more, and this is almost free. If we draw a perpendicular from the point B so that it meets the radius at F, then the length FD or DF, that's the harmonic mean of AB and BC. And once again, it has to be less than BD, and it has to be less than OD. So you've got that lovely relationship. So Pappas developed this in 320 AD. It had obviously been around for a very long time, but he published it and gets the credit for it. And again, Ellen, if you move the point D around, then this is a lovely way to calculate the 3 means. Again, play with this at your leisure. There's an interactive diagram on the web page that we'll reference at the end. Move on, Ellen, thank you. Pappas was a busy fellow because he actually developed and published 2 constructions for the harmonic mean. This one uses the tangent, and I'll leave that one as an exercise for you because we've got lots more to talk about. But we get some lovely, lovely results. And this one didn't come around until the 1600s when Desargues was developing his theory of projective geometry. And it is just simply amazing. It's a construction, what he called the 4 harmonic points. And again, I just came across that by searching, found the reference to harmonic, and I thought, has this got anything to do with the harmonic mean? And yes, it did have. And it's explained in more detail on the web page. So we'll move on. So some lovely geometric applications. We use the fact here that A times B is equal to D squared. The perpendicular, the square of the perpendicular is the product of the feet at the base of the perpendicular. But you know, this little right angle triangle drawn inside the semicircle is also has 2 other nice results that are related. The length of E, that it's no longer a perpendicular, but it still comes off from 2 feet. So E squared will equal A times A plus B, and F squared will equal B times A plus B. So lots of lovely geometry to explore in there. Move on, please. And this is how you can use these results to prove the result on the previous page where we developed the three means. So sorry, it's a very quick run through the beautiful mathematics in both arithmetic and geometry that is linked to this. But I would encourage you, if this is something that you're interested in or you think it might be fun and worthwhile for your students, grab this file and also reference the web page at the end, because there's lots more information there. Now, we mentioned previously the four branches of mathematics to the Pythagoreans: logistica, which was what we think of as arithmetic; arithmetica, or number theory; geometrica, or practical geometry, measuring the earth; and harmony. Harmony was a branch of mathematics to them. But they didn't think of harmony. When we talk about harmony now, our idea is multiple notes played concurrently to give a pleasing sound. No, their definition of harmony was about a well-sequenced progression of notes, not necessarily a pleasing combination played together. So it's a slightly different way of thinking about harmony. Next page, please. This brings us to series and sequences. And, you know, Pythagoras' biggest claim to fame, as far as I think he was most excited when he discovered that take a string and shorten it by nice whole number ratios, and you get these nice sounds, this nice sequence. So the octave is halve the length of the string. Divide the string in the ratio 2 to 3, you get the perfect or major fourth. Divide the string in the ratio 4 to 3, you've got the fifth. Now, they talked about, Pythagoras and his followers talked about these tones and how important they were for all sorts of things, everything from astronomy to health. They believed that this, when he said all his number, this was the basis for that. He was blown away by this. The fact that they talked about fourth and fifth meant that they had ideas for tones in between these. And no one knows what they were. That's not recorded. But we might assume, since he called it the harmonic mean, that that could have been the basis for him building up his scale. Next page, please. How could we build up a scale? And suppose we think of a scale as we do today as, well, just the white keys as 8 notes. Add the black keys and you've got 12 notes before you repeat the progression. Our modern scale was developed in the 1600s, 1681. It's called a well-tempered scale. And that's because the gap between each of the tones is geometric progression that's built from the 12th root of 2. Let's have a look at the chart on the next page. Now, I appreciate it's a bit hard to read.
Again, there's a lot of numbers.
When you grab this, Ellen, you developed this page. Would you?
Yes, I did.
Just quick chat.
I used this to teach my engineering kids because they do some programming of music and they use these frequencies. They are rounded clearly, but it works well enough for them to use in their engineering and play some little tunes. And I put in a keyboard and a violin for people to reference so they can see approximately where the octaves are. For instance, the lowest note on a violin is a G3, and the top string, not the top note, but the top string is an E5, and here's where it would be in the keyboard.
Yep. The one we tend to know best is what we fondly think of as A4, and that's 440.
That's right there.
Right there.
And on the violin, it's right there.
Thank you. So the A 1 octave below will be exactly half of that. So it'll be 220. The A 1 octave above, 440 will obviously be 880, and that's how the scales work. So a note 1 octave above is twice the frequency of its corresponding note. So if we move on, if we were going to try and develop a scale using harmonic rather than geometric mean, and that's where the well-tempered is a geometric scale. Move to the next page, please. So if we look at column B in the spreadsheet here, you'll see Pythagoras's beautiful whole number ratios from 1 to 1, 4 to 3, 3 to 2, 2 to 1. And if we wanted to put notes in between, then one way we could do this might be to take A and E, so 1 to 1 and 3 to 2, and find the harmonic mean of those, which would be a C sharp. Once we had the C sharp, we could use that with the original A to find B. You see where it's going, that the harmonic mean could be used to build a harmonic sequence. And if we click the button there, we add those, we see that most of them come out fairly nice. And if you compare the red columns with the green columns, the red columns are the harmonics and the green columns are the corresponding well-tempered notes. Now we'll see straight away that the original ratios, the A, the D, the E, and the A prime are very, very close. Okay, so Pythagoras with his 4/3, 3/2, 2 to 1, the well-tempered scale fits very, very nicely with that. The ones in between, not so much. But all that means is that the music that the Pythagoreans would have listened to would have had a different sound to ours. Doesn't make it better or worse. Let's move on and see what this actually sounds like. If we've got an Innovator Hub, then we can really get down and do some fun stuff with this. We move on. Ellen's got to remember to, let's show the menus for this one. This is a keyboard that's picked up a hub that Ellen's got there, and just hit a couple of notes on the keyboard, please, Ellen. There we go.
Can you hear them?
Yep, that's lovely. All right, let's play a song. That's nice and clear. So that's using our well-tempered scale. Let's just play that scale, Ellen, sound samples, yep, down to the well-tempered scale B. Yep. All right, now let's play a harmonic scale. If we tuned it differently, sounds different, doesn't it? And it doesn't hit every note on the keyboard, obviously, because our notes don't correspond to theirs. But let's play Happy Birthday now using a harmonic scale. Okay, quite a different sound. I like it. I think it's pretty bluesy and a bit dark, actually. And it's not surprising. Think about it. How does the harmonic scale compare to the geometric scale? Each of the corresponding notes are going to be less because harmonic mean is always less than the corresponding geometric mean. If we tried to develop an arithmetic scale, we'd expect those tones to be sharp. And I've done that in this So lots of interesting things to play with here. We're doing okay for time, so let's have a listen to Happy Birthday play with an arithmetic scale. All right. Hit reset there, Ellen, to go back to our normal scale. And we've got a couple of minutes, so let's take another one just for interest. So what we've got here, let's do, one of my favourites is for release. Now go to the very second bottom one, try harmonic tuning. And we'll play for release again with so the idea of this page, this was developed in Lua, and it offers a range of tools for students to play around with different sounds, different notes. You'll see the direct connection there with the graph as the frequencies are played. I wanted to just draw attention to one other small thing here, and that is that our well-tempered scale is a deliberate attempt to force a discrete way of thinking about music rather than a continuous. And we take it for granted the notes on the scale. The piano is our principal musical, in a sense, musical instrument. It's very much a discrete sequence of notes forced into that, but not every instrument has that. Ellen, you play the violin, and it's very much not a discrete, but a continuous instrument.
Yeah, I could play all those notes if I had to.
Yeah, yeah. And how do you hit the right ones? Is that just feel and experience?
Yes, feel and experience. You just know where it is.
So another tool that we have with the Innovator, if you go to Read Samples, menu 4, every Innovator has a brightness sensor attached to it. You can get other sensors as well. You can get a ranger, a digital humidity and temperature, but brightness is always there. If you go and select Read Brightness, Ellen, all right, now just press on the top half of the screen. Okay.
Let me try. Wait a minute. I gotta set the Innovator back up. Here you go.
Thank you.
I'm moving around and making sure that it gets different lights.
Thank you very much. We've got the problem, of course, that the speaker on the Innovator has to be held close to Ellen's mic speaker, which limits the freedom of movement she's got. If you go down to Timer Samples on the menu and choose Wait 5, it'll play 5 seconds, and if you move it around over that 5 seconds...
Yep, I practiced this. Let's see if it works. Okay,
so your Innovator has become an instrument called a theremin, which, if you've seen it played, is basically you move your hand up and down above the instrument and it plays different tones.
So I can describe what I was doing is I had the Innovator next to my mic, and I was just moving my head all over the place to get the Innovator to read different lights. Hopefully nobody looked in the window at that minute.
So we should have had the camera video on to capture that. But look, this is another gorgeous application for our innovator, linking sound to the readings of different real-world phenomena. Obviously, if you hook up a Ranger, a little ultrasonic motion sensor to your innovator, and you move your hand up and down above that, then you are exactly playing a theremin. The students can experience in a multimodal way the various aspects that you're talking about. So distance, brightness, temperature, and so on. And hearing that. This same idea could be linked, of course, to experiencing functions and graphs. And for that, we're going to, or a possible application, disconnect, please, Ellen. And we move to our last section, which is the idea of doing a little bit of coding around this exploration. So I've written a couple of little programs in TI Basic that you and your students might find a little bit more accessible than trying to code Lua to build a keyboard. So move on to the next page, please, Alan. All right. Now, on the right, you've got a little TI Basic program. I won't go into enormous detail, but basically it builds a list called temp list. Temp list starts with whatever value you begin with. So we're going to begin with things like 220 or 110. And then can you see what it does? It runs through from 2 to 13, so it's going to give 13 notes, and takes each value in turn and adds 1/12 of the start value. So move on. Let's run a Ritz scale at 220. All right. Now each of these notes, if you arrow up onto that, Ellen, and then press your right arrow, you'll see it begins with 220, and as expected, it ends at 440. So you've got one full octave with all the sharps and flats in between. There's 13 notes there, and the first is exactly 1/2 the last one. All the other notes lie at equal intervals between them. So you've built a scale, an arithmetic scale. Beside it, you'll see a very simple little innovator program to play whatever list you put in. And it just, so if we do play, brackets, up arrow, so typing in again, press enter. Now, funny thing, when you use the innovator with the software, there's a pause before it actually does anything, giving Ellen time to put the thing up to the speaker. Very nice, very nice. That pause doesn't occur if you're using this on the handheld, by the way. It's interesting. It's the computer clearing all the various configurations to get through, I guess. So we've got a very simple way here to play different lists of numbers, lists of values, and you can build your own lists. So students can try different tones and then just use the play program to listen to them. We could, for instance, build a list of values for the function x² minus 2 and multiply them by, say, 440 or 220 and see what that sounds like. Kids can actually hear the difference between linear functions, quadratics, cubics.
So Steve, I think there was a question that popped up about playing, and I can't see the chat now, but maybe Mike can see it, about playing more than one scale at a time.
I was hoping someone would ask about this.
Yeah, somebody, I saw it pop up.
Something that, that I'm actually working on at the moment. At the moment, the innovator can't play even if you can connect other speakers. So it has a built-in speaker and you can connect other speakers, but it can't play multiple speakers simultaneously on the one Innovator. However, we are working on I'm working on a little program. If you connect more than one Innovator, then it becomes possible to have them playing. So the first one generates a tone, sends that to the next one, which generates maybe the octave or the fourth or some other related tone, and you can build your chords in that way. So it's a little bit more fussy, I guess, and potentially interesting. If anyone's interested in following this through, by all means, drop me an email, steve.arnold@ti.com, and I'll share as I get further with this.
Or you can do what I did and have two innovators and program a violin and viola Mozart duet, and you have each one play one of them and play them together.
Yes.
It's a lot of fun.
And that's a better way. Have the kids work collaboratively.
Right.
So that you know, they each have an innovator and they're playing tones together, and they'll get their chords that way. So that's a lot less fiddly.
And then there was another question about all three scales. Once again, I can't see the chat window, so
yeah. Well, same problem. Can you play all three together? It's going to be horrendous.
I don't know if they mean at the same time or just play all three. I couldn't see the question, so.
Yeah. Obviously, the little programs, the TI basic programs, you can configure to do all sorts of different combinations of these. So if you move to the next page, we started with the arithmetic scale, even though nobody plays an arithmetic scale, because it was the simplest. We simply add 1/12 to each tone. Now let's look at the one that actually everyone uses, the geometric scale, or the basis for the well-tempered scale. Now in this case, we don't add a constant interval, we multiply by a constant ratio, the 12th root of 2. So it's almost the same program as the first one, but instead of adding 1/12, we multiply by 12th root of 2. Move on. Let's see what, well, here we've already developed the geometric scale. Once again, you can see it begins at 220, ends at 240.
440.
And 440, and the notes all lie between those two values. Obviously, if we went back to our Lua keyboard and played each note successively, which you can use in the arrow keys to move through the scale, that's exactly what it would sound like for the well-tempered scale. If you wanted to compare the values, very quick and easy way on Nspire would be to line them up in a spreadsheet. And you'll see how they compare the arithmetic, geometric. The final little program before we wrap up is not so simple as you might guess. The harmonic scale isn't an equal difference or an equal ratio. So the program to write this would be more of a challenge for your students. I guess my inclination would be to maybe work through the arithmetic scale program with them, so they've got the idea, and then send them on to do the geometric scale if they when they've done the geometric mean. Then the harmonic scale, you can see, is set up differently. Let's have a look at it. Here we allocate those values that Pythagoras knew. So the 6th note in the scale is 4/3 of the beginning note. The 8th note is 1.5 times the beginning note, and the octave will be twice the beginning note. The other values then are the harmonic means of combinations of those. So it's not, you know, terribly, horribly complicated once you've thought it through. So it could be a suitable challenge for a student or a group that was following through on this investigation. If we go on and have a listen to it, we get the Same idea. I guess the question is, why did they go to a well-tempered scale? Why didn't they stick with a harmonic scale? And the problem is that as you go up the octaves, as the numbers get larger, the gap between each note, each tone, gets bigger. So in the 5th octave, the gap between the notes there is going to be much greater than it is in the 2nd or the 1st octave at the low end of the scale. And that's going to mean that notes played together will sound off. You need the geometric sequence to ensure that they're all equal. I wanted to just quickly draw attention. Ellen, have you got the web page up at the moment, or?
No, you mean your web page?
Yeah.
No,
yeah.
I don't. But I think if the link is in the chat window.
Yep. Which Mike has just put there. If you tap on that, Ellen, it should. Okay. Quick look. Now, I did this web page quite a few years back, building on the research that I'd done, so it's got a lot more detail. You notice on at the top of the page, you can download the TI-Nspire document that we've just been using, and I'll keep that updated because even getting ready for this over the last few days, there are about half a dozen bug fixes that turned up. The second link there at the top, I draw your attention to, Ellen, if you just click on that. I mentioned at the beginning that I think of this as one of a type of a perfect problem because it spans both the school years and the various branches of mathematics. And this site here may again be of interest to some people to have a look at. So I talk about our search for harmony, a quick summary and a link again back to the other website. And then there's a few other problems there that don't relate to music, but that you might want to have a look at some stage. So if you if you arrow back to the previous one, there's a tab open for it there, I think, at the top, Ellen. Yep. And you'll see that the sequence here pretty much follows what we looked at with in the session. If you go to a picture of harmony, please, Ellen, sorry. Here you'll see a couple of things. The one on the left, the orange one, uses Java and gives you an interactive one. Now, many browsers and systems don't work, certainly most portable devices don't use Java. On the right, though, you'll find the construction spelled out step by step. So if you wanted to be able to do the constructions that were illustrated, you can follow that sequence there and get the idea of how it's done. If you click on it, it takes you to an interactive document. You need to scroll down a little bit on this one. And so here you can change the values for AB. Well, A is the length AB, and B is the length from B to C. So you can change those values, and that'll calculate your arithmetic, your geometric, and your harmonic means. So those things are there for each of the three constructions. So geometry people, that might be a bit of fun. Finally, at the end, back to the previous one, please, Alan. And scroll down. Go to the Harmony in Perspective link at the bottom. And scroll to the bottom and you'll find references and other websites to, oh sorry, table of contents. There's one more. That's right. Go to an application, number 7. this is an application of the harmonic mean for actually calculating approximations for square root numbers, and it's an interesting technique and might be of interest to do with some students. And the bottom of that page, there are a bunch of links and references. So lots of resources. If we move too fast for you during the session, I do apologise, but I wanted you to see that there's plenty of time to go back and follow these up further. So thank you very much. Thank you, Ellen, for your great assistance in this, and
well, thank you, Steve. That was
sharing
a lot of fun.
my journey.
So let me get back your. There we go.
Okay.
I'm trying to give it back to Mike. There we go. There you are, Mike.
Thanks so much, Ellen and Steve. We're going to begin wrapping things up tonight, so if you have any last-minute questions for Ellen or Steve, please try to get those asked. I know they'll do their best to try and get those questions answered. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback really guides us as we plan future online events. We really listen to your feedback, and so we really hope you share your thoughts in a post-webinar survey. We're excited that this year's T-Cubed International Conference is coming to Chicago in early March. I think it's a great place, for instance, to talk to Ellen and Steve more about this, because I don't know about you, but I think I need a few more minutes to kind of digest some of the things that they were talking about tonight. So the nice thing about the conference is you have that time. It's not just run in, grab a session, and then all of a sudden you just go home and then run back to your classrooms. You have a couple days to sort of chew on things and connect with people if you need to and reconnect. So please consider joining us at the T-Cubed International Conference. And as Ellen mentioned earlier in the agenda, tonight we're giving away to one lucky winner a T-Cubed International Conference registration. And tonight's lucky winner is Patricia Martinez. So Patricia, congratulations. We'll be in touch over email in the next couple of days, but we hope to see you as well as everyone else at the T-Cubed International Conference. To receive a certificate of attendance for tonight, click the link in the chat window. There we go. And if that link isn't working for you tonight for any reason, have no fear, you'll automatically get a follow-up email in a couple days that will have a link to the recording, a link to the certificate, as well as a link to the documents that were used tonight. So not only Steve and Ellen's TI-Nspire file, but also any other information that they found useful. If you're watching this on demand, please go ahead and copy that link into your favorite browser to receive your certificate. After we leave tonight, if you need some post-webinar follow-up, feel free to give us a call at 1-800-TI-CARES or send us an email at ti-cares@ti.com. We'd love to hear from you. Thanks so much, Ellen and Steve, for everything you shared tonight. I really appreciate it.
That was a lot of fun.
Yeah, thanks very much. Thanks for the opportunity, Mike.
And again, thanks everyone. We hope to see you back online later this week. Have a great night.